Okay guys, so today we're going to do lecture 21, which is going to be second order ordinary differential equations, ODEs. Alright, so in general, a second order linear constant coefficients homogeneous ODE is of the form A d second derivative y of t dt plus b dy of t dt plus c y of t equal to 0. Okay? And let's call this equation A for now. Now, the general solution of the above equation can be either y of t equal to e lambda t or y of t equal to e minus lambda t. Okay, I'll let you go and check yourself. But over here, just for consistency with the first order ODE, we're just going to do the future derivation using this expression here. So let's just say like, let us select y of t equal e lambda t for further work. Okay, so what we're going to do is assume the solution to be y of t equal to e lambda t. So that will mean that dy dt of t, which will be y dot of t, will be equal to what? Lambda e lambda t, and the second derivative will be lambda square e lambda t. And I just realized that I forgot here to put the square to that equation. So now what I need to do is substitute these expressions into the original second order ODE. So substituting into A, what do we have? So the first term will be A unchanged. Now the second derivative will be lambda square e lambda t plus b dy dt, which is lambda e lambda t plus c y of t, which is e lambda t, and this is equal to 0. So we can just rewrite that equation if we factor out by E lambda t as what? A lambda square plus B lambda plus C equal to 0. Okay? So now, this is basically the same thing as the first order. We assume the solution, you substitute, and now you need to say when is this equation satisfied. Okay? So in this case, what do we know? E, the exponential function, basically this means it is always different than 0. If you plot the exponential function, it's never equal to 0. Okay? So then what is the only case possible now for this to be equal to 0 is that the term within the brackets is equal to 0. So the equation, I'm going to rewrite it on top of this page. A lambda t of A lambda square plus B lambda plus C equal to 0 is equal to 0 if and only if we have A lambda square plus B lambda plus C equal to 0. Okay? And this equation over here is what is generally called the characteristic equation. Okay, so basically this will be equal to 0. We need to solve for the roots of this quadratic equation. So solving the quadratic equation, for the roots that in this case will be eigenvalues. So what do we have? We're going to have that lambda 1, 2 will be equal to minus b plus minus b squared minus 4ac divided by 2a. Okay. Okay, so now we need to look at different cases, because when you solve this quadratic equation, you can have either the roots lambda 1, lambda 2 are both of them positive, okay, or real numbers. Both of them are real numbers. The other case will be they can be complex roots, or they can be equal to each other, which is called repeated roots. Okay, so let's see what would happen for each one of those three cases. So case 1, if lambda 1 and lambda 2 are real roots, okay, then what happened? Remember the general procedures that once you find the roots, you go back to the assumed solution, which in this case is y of t equal to e lambda t, and because of the principle of superposition, what we're going to have, y of t, so general solution, y of t could be c1 y1 of t plus C2 Y2 of t. This is the principle of superposition, but in this case, for us is what? Since we have two roots, we can have C1. Our assumed solution is E lambda t plus C2 E lambda 2t. Okay? So this is the solution when the two roots are real. Second case, if lambda 1 and lambda 2 are complex roots, so what does that mean? That means that lambda 1 could be of the form alpha plus I beta, and alpha 2 could be of the form alpha minus I beta. Okay, well, these will be the two complex roots. Okay, so now again, using the principle of superposition, what do we have? Y of t is equal to y1 of t plus y2 of t. So again, what is the meaning of the principle of superposition? Is that if y1 of t is a solution of the ODE and y2 of t is a solution of the ODE, the summation of both of them is also a solution to the ODE. Okay? So basically this will give what? This will give us that we go again and substitute in this one. I'm not going to put constants yet. It will be E lambda 1 will be alpha plus I beta plus, oops, I forget the t over here, plus E of lambda minus I beta t, okay, will also be a solution. Okay, so I'm doing all this stuff because what happened is that we could leave the solution. I could just put a C1 here and a C2 here, and this will be a valid solution. But I think our idea will be that since we started just with real numbers, to try to write down a solution just in function of real numbers. So that's why I'm going through this type of little algebra over here. Okay, so this is the expression, and that will be page 151. I forgot 151. So page 152. Now what I'm doing is using Euler's relations, which are what? I'm sure you remember this expression, EI theta is equal to what? Cos theta plus I sine theta, and E minus I theta equal to cos theta minus I sine theta. Okay, so if I use these two expressions and rewrite this equation here, okay, what do we have? I'm gonna have y of t is equal to what? E lambda t of cosine beta t plus I sine beta t plus E alpha t cosine beta t minus I sine beta t. Okay, maybe I should add here one thing. I'm sure you know that, but you know that E of AB equal E A E of B, okay? Just in case I separated just this one here. Okay, so let's see. Oh, I almost got lost over here. So if you do the summation, I don't have to expand, you can see that this term will cancel out, and this will give that y of t is equal to 2 e alpha t cosine beta t. Okay? Okay? So this could be one of the solutions. Alright? So this is a solution of the second order ODE that can be rewritten as, so basically if I divide, so let's say u of t is equal y of t over 2, it's just a constant, so you can do whatever you want with constants, will be e alpha t cosine beta t. Oops guys, before we go to the next page, we continue at just part 1. This is a plus b, okay? Sorry for that. All right. So again, so this will be one solution. So another solution now could be if instead of doing y1 plus y2, we can do 1 1 minus y2. So let's say a second solution can be obtained again by using the principle of superposition. So let's say y of t was equal to what? y1 of t, but before we put plus. Okay? But if we actually put a minus, the principle of superposition also works. Okay? And in this case, what will you have? You will have e lambda t as before, so it will be the same as before, cosine beta t plus I sine beta t, but now will be minus e lambda t of cosine beta t minus I sine beta t. So in this case, what will happen is that this term will cancel out, and you will end up with what? 2i e alpha t sine beta t. So again, this is a solution following exactly the same procedure as before. This is a solution of the second order ODE that can be rewritten as, let's say, v of t, same thing we had before. This time will be y of t divided by 2i. Okay, this is just a constant. And then this equation here will become e alpha t sine beta t. Okay, so finally the general solution for complex roots is given by y of t, you can add both of them, will be c1 u of t plus c2 v of t. So I need to go to the next page. (153). So this will mean that y of t is equal to c1 exponential alpha t cosine beta t plus c2 exponential alpha t sine beta t, or we can just compact the solution and write it down as e alpha t. We factor out by e alpha t of c1 cosine beta t plus c2 sine beta t. And this will be the general solution for complex roots. Okay, and the last case that we need to look at is case 3, is when the two roots are repeated. So if lambda 1 and lambda 2 are repeated roots, then the general solution will be what? So general will be what? We should have y of t equal to c1 e lambda 1t, and then the second one should be c2 exponential of lambda 2t. But that will be, since alpha 1 alpha 2 are the same, will be repeating the same thing. Okay, so in order to differentiate the solution, what will need to happen, then you need to multiply this by t. You can do the proof, but it will take a couple of pages, and I don't think it will add much to the understanding of the problem. Okay, so just one more thing I want to add. So in all three cases means that the roots are real, the roots are complex, or they are repeated roots. The constants c1 and c2 are determined from, let's see, A, initial conditions. This is if it is an initial value problem. Okay, so initial conditions, so we can write down here initial conditions. You will have y of 0, let's say, will be equal to a constant y of 0, and then you can have dy of t of 0 equal to some constant. So this will be, if you think about it, this will be deformation. What is the first derivative of the deformation? Would be some velocity, and then this really becomes an initial value problem, okay, as we have done before. Or what can happen is that you can determine the constant sum from boundary conditions. It's basically the same thing, but it's just slightly two different type of problems, in which you can have y of x1 equal, let's say, to y1, to a constant, and y of x2 equal to y of 2. And actually you can even give the dy of 2, okay? It would depend on the problems. And this will be a boundary value problem, or BVP. Okay, so for example, the initial value problem is generally obtained, for example, for vibrations. And the boundary condition, let's say you need to calculate the deformation. In this case, you need to know, let's say, the initial deformation at two different points, so you can obtain the value of the constant C1 and C2. But the procedure is the same. Basically, you need to have some conditions in order to determine the constants C1 and C2. Okay? Just one quick note over here is that okay, so I see initial conditions, and so initial conditions, more than boundary condition, I always give them at 0, but they don't have to be at 0. You can give them at any time, okay? So initial conditions can be given at a different time than 0, okay? But what happens is that it's always more convenient, because what is the exponential of 0 is 1. Otherwise, you need to do a little bit more algebra. Okay, so let's go to the next page, page 154. So now, what if the second order ODE is non-homogeneous? Okay, so that means that the second order ODE will be of the form plus b dy dt of t plus c y of t. And now we're going to have here a function, let's say, r of t. Okay, so if you had vibrations, this is really similar to vibration. That's the type of problem you will solving over and over. Okay, but here we just do it from the mathematical point of view. So in that case, you will see that the solution y of t highly depends on the forcing function r of t. So if when taking vibration, you're probably solving, working with probably two blocks connected by springs. Let's say you had two masses connected by different springs, and one of them could be subjected to a forcing force. So obviously the forcing force is the one that will be guiding the response. It's just like if you have somebody having two blocks connected by a spring and somebody's moving it, the response is basically going to depend on the movement of the forcing function r of t. Okay, so what is the general procedure? So you need to say the solution y of t might be separated into a homogeneous part and a specific part. So basically you have the homogeneous part and a specific part. So that means that the assumed solution will be of the form y of t will have two parts. Y homogeneous of t plus y specific of t. And again, this is valid. This is like, again, applying the principle of superposition. Okay? So what's going to happen here? Such that obviously y homogeneous need to satisfy the homogeneous equation. So such that y homogeneous of t satisfies a homogeneous dt. I'm gonna skip putting the t plus b dy homogeneous dt plus cy homogeneous equal to 0. So that's the first problem that we solve. Okay? And the solution ys of t depends on the nature of the forcing function r of t. Okay, I'm going to go to the next page. So continuous. Next page is because I want to be able to put everything on the same page over here. All right. So page 155. So let's see. So let's say first this is a polynomial of degree, and I'm trying to see if I'm going to be able to fit it here. So here will be a column for r of t, and in that case y of t will be k0 plus k1 of t plus kn t of n. Okay, so let me give you a quick example. I'm going to give an example for every single case. So in this case, let's say r of t is equal to 3t squared. So that will mean that y of s t will be equal to k0 plus k1 t plus k2 t squared. Okay, and I will tell you how to find those constants afterwards. So this will be y specific of t. So this is our case 1. Case 2 is an exponential function, so exponential function with let's just leave it as exponential function, otherwise I'm going to run out of space. So let's say the solution will be in that case k naught e of capital omega t, where capital omega is what is known as the forcing frequency. So let's give an example. Quick is the easiest one. So let's say r of t, let's say, would be equal to 4 exponential to minus 2t. So in that case, the y specific of t will be equal to k naught exponential of what? Minus 2t. That's it. Okay? Wherever you want here, but omega, here's what is known as the forcing frequency. That's the same name they give in vibrations. Alright, so 3. This could be given as a trigonometric function. Alright, so in that case, the solution will be what? K naught cosine omega t plus k1 sine omega t. And in this case, this will also be the forcing frequency, but I'm using lowercase omega. You will see why on the fourth case. Okay, so let's give a quick example. So let's say r of t in this case could be equal to 2 cosine 3t, so that the solution y specific of t will be equal to what? K naught cosine 3t plus k1 sine 3t. And finally, the fourth case will be basically the summation of these two. So it will be exponential plus trigonometric function. Okay, so in that case, the solution would be of the form e omega t k naught cosine omega t plus k1 sine lowercase omega t. And if I give you an example, let's say r of t could be equal to 4 exponential to minus 3t times sine 2t. So in that case, the specific solution will be exponential of minus 3t times what? K naught cosine 2t plus k1 sine 2t. All right, so okay, so this would be our table over here. Okay, all right, so in this case, now we need to know how to determine those coefficients: k naught, k1, kn, k naught, k1, and k naught, k1. Okay, so the coefficients cannot